Swayam Prabha. Digital India. Educated India.
Hello, so welcome to this course in astrochemistry, and this is lecture 19 today. So from the last classes, we looked into a list of molecules from amongst the ones detected in the interstellar medium, and we saw their structural variety. We looked at how, ranging from small organics to small inorganics to medium-sized organic molecules, we can have a diverse structural array of molecules which can be detected in space. So we looked at the possibility of chemistry, each of those different structures present, and in the context of carbon-containing species, we understood that the species containing more than 4 atoms, carbon-bearing species which contain more than 4 atoms, are themselves called as complex organic molecules. Now this name is reasonably justified because complexity need not be just in the number of molecules present, but it can also be in the structural form. For example, we looked at the example of C3H, I think, where a cyclic structure was possible, a cyclic alkyne structure containing only 3 carbons. We discussed that, and also a linear structure wherein a divalent carbon as its isomer was also noted in the ISM. All right. So the overall idea is that there are reasonably many molecules detected in space. So the chemistry of space now is therefore an active area. So, but then I stopped the previous lecture by asking you this question. How, of course, are these molecules detected in space? Why should you take my words for granted? I mean, I'm giving a lecture here and I'm teaching you that a lot of molecules exist in space. So just because I tell you folks, why should you take it for granted? And I've asked you to take it for granted all along, right? Now the time has come to slowly unravel all the aspects which actually prove that molecules and atoms exist in space. Now, as part of this venture, let us actually, try to go back in time. Let us go back approximately 200 odd years. Okay, let's assume that. Okay, right? So, in approximately, let's say, 1820s or 1810s. Don't worry about the exact years. Okay. Now, let's assume that we're in this era. What do we know about the nature of light? I will tell you why this question is pertinent. Okay. We understood that by around this time, light was suggested to be a wave. Okay. Light is suggested to be a wave. And although what exact medium that light needed was not settled until much later, but around this time, light was known to be a wave, and 2 characteristics, or in fact 3 characteristics of wave are found to be its wavelength, its frequency, and its amplitude. Okay, so we know that light is known to be a wave. Okay, as of 1810s or 20s. What is also known was that if you pass light through a prism, what happens? Light gets split. If you pass white light, okay, what is conventionally called as white light. For example, you pass light from an LED bulb today, or even if you take the example of sunlight, right? So sunlight, you pass through prism. Now, what's a prism? I'll leave it to you as a homework. You should know this from high school. So what is the material that a prism is made up of, and what are its properties? Okay, that is something I can give you as a homework and you can figure out on your own. Okay, but because this is common knowledge from high school, so when you pass sunlight through a prism, what happens? You get, what do you get? You get a continuum of different colors, right? You get the sunlight which is split into different colors, and you get what is called as a spectrum. Now, and what are the different colors that you notice? You simply notice, right? In this order. Of course, I'm using white chalk, but I'm just noting the colors with the letters V, I, B, G, Y, O, R. Okay, I mean, so it's just a rough representation. V stands for violet, indigo, blue, green, yellow, O is for orange, and R is for red. Okay, you get a spectrum with our understanding of the word spectrum meaning some sequence of colors. And it is a continuous sequence of colors. All right, this is a sequence, sequence. All right, so you get a continuous sequence of colors. Are we all good? Yeah. So with this understanding, now let's say you do the same experiment. You let sunlight come to a very tiny aperture from a window, and then you place a prism. Now, approximately around the same time, in the early 1800s, someone noticed that the sun's spectrum. What do I mean by spectrum? It is the sequence of colors that is obtained after passing sunlight through a prism. Okay, right? Was not continuous. And some specific dark lines. Please note this point. Okay, specific dark lines at well-defined wavelengths. Okay, at well-defined wavelengths were noticed. Well, so what am I talking about? You split sunlight through, pass it via a prism, and then you get the different colors. However, this stretch, right, it was actually not found to be continuous. Instead, say for example, there was a dark, I've just rubbed off some part here. There is some dark line here. Let's say there's some dark line, and some dark line. So initially, if you simply split it, you wouldn't notice it. But if you carefully perform the same experiment, right, you would notice that some well-defined dark lines at, again, defined wavelengths, at finite wavelengths. For example, if we look at the VIBGYOR sequence, the wavelength corresponding to the violet part is what? You should be knowing from your discussion on the electromagnetic spectrum in physics and chemistry, correct? What is it? It's of the order of approximately 400 nanometers, right? Or 400 nanometers. And the red one is approximately around 700 nanometers. Okay, and as you go from V to R, the energy decreases, remember. Okay, recall that your E is hc over lambda. As you must have encountered in several introductory chemistry textbooks, we'll also go through the same formula in the context of astrochemistry also in this course. All right, so at well-defined wavelengths, right? So each of these colors corresponds to a different wavelength. Okay, now at well-defined wavelengths, you have intense dark lines, which makes this spectrum not continuous. All right, please note it. So discrete lines which make the spectrum not continuous, and this was obtained only by a careful observation of the sun spectrum. And approximately in the early 1810s, right, around 5 such lines were noticed. Okay, so please hold on. Now, you must be wondering, why in the first place should we expect a continuous spectrum? And then, why is it that there are dark lines? So there are two questions, right? So hold on to these questions. We shall, peel the fruit or vegetable layer by layer. Okay, so I'll give you answers to all the questions. For now, just note the experimental observations. Okay, here comes the main part of the story. It is that, now this was in 1810s. This is the knowledge around 1810s. Fast forward to 20 years, around 18 30s. Okay. A German, he was not a scientist by profession, he was rather a craftsman. Okay. Fraunhofer. I presume my spelling is correct, but if it's wrong, please do a spell check. Okay. So Mr. Fraunhofer, now what he did was, he again, like recorded the sun spectrum, but this time what he did was, he used a combination of a telescope, okay, a prism, and a diffraction grating slit or element. All right. So what does the telescope do? What is the telescope used for? To look into faraway objects. Okay. We will again come back to what a telescope does in greater detail in a few lectures down the line. So a telescope to look into faraway objects. What about a prism? Well, the prism is for, of course, dispersing. Now what is meant by dispersing the light? By dispersing, I mean splitting of light. This phenomenon is also called as dispersion. And why do you need a diffraction grating slit? What's diffraction of light? It is that, it is the bending of light around some corners, right? That is what is called as diffraction. If you have a finely grated diffraction slit, right, you can actually understand, okay, you can get the same spectrum with much better resolution, okay, right? So to get much better resolution in the spectrum, now what did Fraunhofer do? He used a combination of a telescope, prism, and diffraction slit taken together. All right, this combination of telescope plus prism plus a diffraction slit is overall called as, I'll just call this T, P, and D. All right, this combination of T, P, and D was what is actually called as a spectroscope. Please note this phrase carefully. We are going to be, repeatedly using this phrase again and again hereafter. A version of this. We're going to be using the phrase spectroscopy, okay, in a slightly different context, but the stage is set, okay, for the use of this word. Now, what does it enable one to do? It enables one to look at faraway objects, get their spectrum, okay, right, and get them with tremendous resolution as well. All right. So it was Fraunhofer's innovation in the instrumentation which actually enabled us to understand so many things, which I'll tell you very soon. What exactly are the things we'll understand? That's a suspense for now, but I'll tell you very soon. Okay. Now, what did Fraunhofer observe? Fraunhofer actually observed that, see, we call in around like 1810s, there were 5 such dark lines noticed in the sun's so-called continuous spectrum. It was not so continuous after all. 5 well-defined dark lines. Okay. Fraunhofer actually noted approximately 575 such dark lines. So 575 such dark lines were noticed in the sun's spectrum. We need not go into exactly at what all wavelengths. That is not pretty much relevant for our purpose, but this is a key observation. There were just so many dark lines. It is not just a continuous spectrum of various colors obtained, but on top of 5, there are actually 575 dark lines. That is because he could get a much better resolution in his instrument. Are we good? Are we good about the progress so far? What's the overall objective? To actually find out how molecules are detected in space. For that, we're starting off with sunlight, and we have not yet discussed any molecule yet. Okay. Now we're going to come to that stage very soon now. Now this is what? This is approximately in 1830s, right? Now fast forward to roughly 30 more years. Around the time of 1860s, two scientists, I believe Kirchhoff, the person of the Kirchhoff's law fame in both thermodynamics as well as in electrostatics, that Kirchhoff, and the Bunsen of the Bunsen burner that you see in chemistry labs. Okay. Now, what these people were doing, they were actually heating various elements. Okay, right? Such as, for example, you talk about like potassium, sodium, copper, hydrogen, ... Okay, they were heating various elements on Earth. Okay, of course, on Earth, we've taken a small break from the sun. We'll come back to the sun very soon. Okay, so they were heating various elements on Earth, and they found that, let's say, for example, you heat sodium. Once you heat sodium and you record the light, you record the spectrum. What is a spectrum? A spectrum for us is nothing but a sequence of colors, right? A sequence of some colors. So you record the spectrum of, let's say, heated, let's say, for example, sodium. Okay, right? Also heated sodium, and you found some bright lines. Okay, right? Some bright lines were noted. Heated, it can be any element in general. It need not be sodium. It is whatever element they took in their experiment. Okay, you see bright lines, and again, what type of lines are they? They are bright lines which are discrete and at well-defined wavelengths. I'll write it here. Well-defined wavelengths. So please note this. Okay. So what is the experiment we're talking about on Earth? We're talking about, like heating up an element, heating up some element, right? And it is going to emit some radiation. So once it emits its radiation, you can again, pass it to a prism or do whatever, right? By do whatever, I mean like do a similar such setup that we did for sun, and you record the spectrum. When you record a spectrum, right, you see well-defined bright lines. Well-defined bright lines in the case of the heated elements, they are discrete and they're also at well-defined wavelengths. Okay, are we good? Now, this is the experimental observation on Earth. Now, Kirchhoff and Bunsen, they had known about the experiments performed by Fraunhofer, approximately 30 years earlier. I mean, between 1860 and 1830s, right? Now, what they noted was, for several elements, right? For several elements, the bright lines occurred at exactly the same wavelength as some of the dark lines noticed from sun spectrum. Now, isn't it fascinating? You have, some light observed from sun. What is light? It's after all some radiation emitted by sun, correct? And you saw some dark spots. And you see it at some wavelength. Now, in an apparently unrelated experiment, where like people performed by simply heating elements and recording their spectrum, you measure bright lines, okay, right? And these bright lines, they happen to be occurring at exactly the same wavelength as the dark lines from the sun. Please note this. So, human intuition tells us that, well, there must be some connection, right? There must be some connection between the lines, the dark lines, and the bright lines over here. Now, what exactly is the connection? To do that, again, Bunsen and Kirchhoff and several other scientists also, roughly around the 1860s, what they did next was, this is page 7. They actually they took a, let's say, you take some source of light, okay, source of, I mean, it is some incandescent light, right, okay, right, some light bulb in the lab, and recorded its spectrum. Now, once they recorded its spectrum, they noticed that it was a continuous spectrum. Please note this point. Continuous spectrum, and did not contain any dark line. All right. So it was a continuous spectrum that they obtained without having any dark line. This is a point to be noted. Okay. Then what they did was, they actually, let's say, this is a source. I'll just draw it here. This is a source. Okay, this is a source of light. If, they let the light, okay, right? They let the light pass through. They let the light pass through some gas. Okay, some heated element, right? Yeah, source of light. Okay, and let's say, this is the path in which light is going, and in its path they put a heated element. And then recorded its spectrum. Okay. Now what happened was, the continuous spectrum became something like this. In other words, okay, right? In other words, you see a dark line. I'll just mark this point as dark line. Right here. Okay, right? So you see a dark line at a well-defined, a discrete dark line at a well-defined wavelength was again noticed. This is a continuous spectrum and a discrete dark line. This is case 1 with no gas, and this is, or like no element over there. I'll put it like that way. No heated element. And this is with the heated element. So this is with the heated element. All right. So what do you notice? You notice that it was again a continuous spectrum. Okay, a continuous spectrum. You pass it to a prism, and then you get the different colors and all of that. And once you let the light pass to a heated element, right? A heated element which is typically in the vapor phase. You see a discrete dark line in point. I'll just call this D. D for dark. Okay, right? In an otherwise continuous spectrum, you see a discrete dark line. All right. Now, again, the next observation that the scientist made was that the discrete dark line, okay, the wavelength of the discrete dark line, I'm just going to call it D for dark, okay, right, was exactly the same as the wavelength of the bright line, okay, right, obtained when they heated various elements and recorded its spectrum. Are we clear, right? So this is when spectrum of heated elements, okay, right? Now this dark line, okay, right, obtained by letting the heated element, letting light pass through the heated element. Do you understand the difference? Of course, in both the cases, the elements were heated and typically in the vapor phase. But the key distinction is that over there, the spots that were obtained were actually only due to these elements, okay? But over here, in other words, amidst a range of continuous dark stretch, you would see bright lines, okay? But in this case, you first record the spectrum of light itself, and so this is going to be colorful, okay? And then you just place the heated element in the path of light, so you get a discrete dark line. So the discrete dark, the wavelength of the light, the wavelength of the discrete line obtained in this case when you place a sample in the path of light is the same as the wavelength, the wavelength of the bright line, okay, the bright line obtained when you obtain the spectrum by heating various elements. What do you conclude from this? What do you conclude from this is that, well, okay, in the previous case, that is when the elements were first of all heated, and then we were recording their spectrum, they emit light, okay, right? So in this case, I'm going to call this like the bright case. In the bright case, B for bright, okay, bright elements emit light, and that results, okay, that results in the bright lines. Now, if the same element, okay, right, absorb light, okay, in the case of darkness, in the case of the dark lines, elements absorb light, and so you get dark lines. And because if you're talking about the same element, okay, if you're talking about, for example, a sodium the spectrum of sodium being recorded here versus the spectrum of, versus being sodium gas being placed in the path of light here, vaporized sodium or a flame of sodium kept in this path of light, okay, you see that we're talking about the same element. So the same element, when it absorbs light, right, you get a dark line. And the same element, when it emits light, you get a bright line. And because the element is the same, the wavelength at which it absorbs is the same as the wavelength at which it emits. Are we clear? So in short, okay, a hot gas emits light, and so you get a bright line, right? And the same gas, when it absorbs, I would say hot gas of I would just say some hot element instead of, by element I mean the elements of the periodic table, and the same element, as it absorbs light, you get a dark line. Because the element is the same here, the two wavelengths, the wavelength of absorption. Now instead of using like D and B, I'll just call it lambda for absorption is going to be the same as lambda for emission. All right. So to sum up, in this class, what did we see? We saw that Fraunhofer obtained several dark lines in the sun spectrum, right? And to follow up on what Fraunhofer did, several experiments were performed by recording the spectra of elements known on Earth, and we see that the wavelength at which an element absorbs light is the same as the wavelength at which it emits light. Only that in an emission spectrum, the line is going to be bright, and that in an absorption spectrum, the line is going to be dark. All right. So we stop here on this note. In the next lecture, we shall continue with this and see how this idea is going to be helpful in understanding what happens in sun and to answer our larger question as to how exactly are molecules detected in space. Thank you.